So let's do experiment. We have a current scale at the 20 milliampere. It's a DC current because we have a continuous source of radiation. And now what I will do is move this source from far away to closer to the detector, photosensor. So I will do it very slowly, and you will see this value will start increasing. So as the distance is reduced, so I'm changing R over here, small r, which is the distance between the source and the point where we want to measure the power. Okay, so I'm changing it slowly, trying to do it slowly. I hope you will be able to read the scale. Methodology is the same. What you need to do is freeze the frame, measure the distance from here, write down the current value. Then do another freezing of the frame and write down the value. Okay? Take as many points as possible. Because you have to do a linear fit, you need to have large number of points so that you can see you get a straight line when you plot current versus 1 over d square. Okay, so what I'm doing is I'm going close to the photosensor once, and now I will start coming back. So look at the current value. I hope you can see it. So now I'm coming back. That you will also use in your experimental data. If I were you, I would do the distance once going closer to the source, and the second time when I'm retrieving at the same distance. So I'll take the average of the current at both points. Okay, so and what you have to do is you have to align with this one to measure the distance. And remember, there is always an error of 3 to 5 millimeter. You have to take into account that one when you are to plot the error bars. Okay, since I'm doing it manually, so sometimes I'm much quicker than, and at times I'm slower. So here we are. I hope we got the same values of current. If it is not the same when we are going and when we are coming back, you have to think what may be the problem. Okay, so that's the experiment. अब आपने करना क्या है? You make a table of distance versus current, and then in the third column take d square, and in the fourth 1 over d square. So 1 over d square is going to be x-axis and current is going to be y-axis. And then plot this one, take the slope of this one, and this slope. From this slope you should be able to determine, number one, this should be a straight line. Find out if there is error, if it's not a straight line. You have to think what are the factors which can contribute कि ये straight line नहीं है. Once you have this slope, if you work out on the Stephan-Boltzmann law, which we determined from the Planck's radiation law, you'll find this slope has a direct relation to the temperature of the source. There are two ways of measuring the temperature of the source. I can have a thermocouple over here and I can measure, but then for a radiating body to radiate certain amount of energy, it requires a temperature, as we know from black body radiation theory. Okay, so you can determine the temperature, number one, from using the Stephan-Boltzmann law, and the second, Wien's law. So if you take the spectra of this halogen lamp, if you look into, you search it, you'll find out its peak is at around 2000 or 2500 nanometers. Okay, so if you take the peak of the spectra and use the Wien's law, you can determine the temperature of the lamp as well. So I would like you to do these two exercises. Determine the temperature from Stefan-Boltzmann law and determine the temperature from the spectrum. Unfortunately, we don't have spectrometer which can go beyond 800 nanometers, so that we cannot get the peak of this tungsten halogen lamp, which is an IR, but you can find it on the web and take this and find out where the peak is. Use that wavelength to determine the temperature and see if these values are close to each other or not. There is quite a possibility these values are not close to each other. In fact, they will not be close to each other for various reasons, and you have to think about those reasons. Okay, good luck.